We're starting chapter 13 today, which is where we start to think about what integrals may have to tell us about things in R3. So we know how to find partial derivatives. Now we want to talk about partial integration. All right, so we have our regular old integral sign, and we are going to have a function sitting inside the integral, and then you either have dx or dy, and that tells you which variable you're integrating with respect to. So our integral f of xy, this might look like an integral of xy squared dy. That's indicating to you that y is the variable and x is going to be treated like the constant. So I would just let x go along for the ride, and then I would integrate y squared like I normally would in Calc 1. I'm just going to make y cubed over 3. And this is an indefinite integral, so I'd put like a plus c on there. If there were limits, we'd draw the line and plug them in. We'd plug them in for y because y is the variable. Likewise, if I had the same integral, xy squared, but then I had a dx at the end, this is indicating that now x is the variable of integration. So we're going to integrate x, and we're going to treat the y squared like a constant. So we're going to let x squared over 2 is our integral, y squared, the constant going along for the ride, and then we would put our plus c on the end. Or if we had limits, we could evaluate them plugging in for x. Usually when we do integrals of functions of two variables, we actually integrate with respect to one variable and then the other one right afterwards. All right, so we might integrate with respect to y, but then when we're done, we'll turn right around and integrate with respect to x. So when we do this, we get what we call an iterated integral. All right, so we would start off, maybe we've got limits, maybe we don't. We've got our function like we had on the last slide. We would integrate with respect to y, and then when we're done with that, we would turn around and integrate the whole thing with respect to x. So we would integrate this, we would have different limits possibly, dx like this. All right, so that's what this notation is going to mean, that we'll do the inner one first with respect to y and then x, or it might go the other way around where dx is on the inside and dy is on the outside. We don't actually usually write this big set of brackets. We'll just say CD, AB, we'll have our function in the middle, and we'll understand that this means integrate with respect to y first and then integrate with respect to x. All right, so let's just do one of these to get an idea of how they work out. So this one has limits. It's got a function 8x cubed y, and it's got a dy followed by a dx. We're always going to look at that inner integral first. The 0 to 3 integral and the dx are going to follow along like bookends until I'm all done with my integration with respect to y. So I'm just going to copy that 0 to 3, and then I've got my function 8x cubed y. I'm going to integrate that with respect to y. So the 8x cubed is just going to go along for the ride, and we integrate y as the variable, y squared over 2. And then we're going to evaluate that from 1 to 2. Usually we would put that line on the end. I think it makes it a little bit more clear if we use those square brackets when we're doing double integrals, so that's usually what I'm going to do. And then hanging out at the end, I've got this dx, which indicates I've got another integral to do when I'm all done with this y integral. Let's simplify what's in the brackets to make this look nicer. The 2 can divide into the 8 and give me a 4. So I've got the integral from 0 to 3, 4x cubed y squared from 1 to 2, and then the dx hanging out there. All right, so remember that we integrated first with respect to y. So that means that the 1 and the 2 limits belong to the y variable. So we're going to plug in y equals 2, y equals 1, and subtract them just like we did in Calc 1 and Calc 2. So I've got 0 to 3, plug in the top limit, 4x cubed, then we'll get y squared, and then subtract, plug in the lower limit, 4x cubed, and then 1 squared. And again, all the while that 0 to 3 and dx are hanging out like bookends at the beginning and the end. All right, so let's see what we have left. I've got, let's see, this is a 4 times 4, that's going to give me 16, and then 4 times 1 will just give me a 4. So I've got the integral from 0 to 3, 16x cubed minus 4x cubed, which I can of course subtract and make into 12x cubed. All right, so when you've plugged in y in the end, you're just going to have the x's left to evaluate. This is an integral that we could do back in Calc 1, right? So we're going to let the 12 go along for the ride, x to the 4th divided by 4, which will plug in 0 to 3, simplify a little bit. I get 3x to the 4th evaluated from 0 to 3, and then we plug in 3 and 0 and subtract. So 3 times 3 to the 4th minus 3 times 0 to the 4th. Let's see, 3 to the 4th is 81 times 3 is going to be 243 minus 0, and we get 243. All right, and that 243 is going to have meaning to the function 8x cubed y. We're going to deal with that in section 13.2. So I've got one more example to show you in the next video, plus a neat trick we call Fubini's theorem.